In this lecture, we'll have a look at some important concepts of the ADL models, namely the long run and the short run effects. So let's start with a simple ADL model, the 0, 1. Remember, the ADL 0, 1 is the following. Yt is equal to beta 1 plus beta 2 xt, and we have one lagged explanatory x variable. So plus gamma 1 xt minus 1 plus an error term. If both of these variables, xt and xt minus 1, are exogenous, then we know that the expected value of yt conditionally on xt and xt minus 1 is the part between the equal sign and the error term. So that's beta 1 plus beta 2 xt plus gamma 1 xt minus 1. That's the value I would expect for yt conditionally on knowing the values of x today and xt minus 1 in the previous period. As a simple example, suppose that yt is the revenue of a firm at time t. xt is the amount that we spend on marketing this week, and xt minus 1 is the amount that we spent last week. So according to this model, the expected revenue depends on what we spend this week and also on what we spent last week. And the argument could be something like people taking part of our advertisement last week still remember this advertisement, and that will affect sales even in this period. So as you can easily see, the derivative of this expected value of yt conditionally on these guys with respect to xt, that's the derivative of this with respect to xt, well, that's just this parameter beta 2. That would be the expected increase in revenue this period if we increase the amount on advertisement this period. So it's kind of the instantaneous effect on the expected value of y when we change xt this particular period. This is why we will simply call this the short run effect. The short run effect of x on y. Now it's not the long run effect, because we also know that if I change the amount that we spend on advertising this period, it will have an effect in this period, but it will also have an effect in the next period. So beta 2 is not the long run effect, but it is the short run effect. So to think about the long run effect, we'll instead look at the unconditional expectations. So the expected value of yt, just take the expected value on the right hand side, is beta 1 plus beta 2 expected value of xt plus gamma 1 expected value of xt minus 1 plus the expected value of the error term, but we assume that that's 0 due to exogeneity. Because of the stationarity assumption, we assume that these two are the same. The expected value of xt is the same as the expected value of xt minus 1. So this is beta 1 plus beta 2 plus gamma 1 multiplied by expected value of xt. So if I now look at the change in expected revenue for this firm, given that I change the expected value of xt. So the way to think about this ratio is simply that I increase the amount that I spend on advertising by 1 unit for all periods of time. And the question is, what will be the corresponding increase in my revenue? We can easily see that by doing this derivative, if I differentiate with respect to this one, all I'm left with is the constant. So this is beta 2 plus gamma 1. Since I'm making a permanent increase in xt and I'm looking at the permanent increase in yt, we will call this the long run effect. It's the long run effect that X will have on Y. The long run effect will be a combination of the short run effect, but this gamma one, which is the effect of the X variable in the previous period on the expected revenue in this period, will also play a part when we look at the long run effect that X has on Y. Now I can easily generalize this whole idea to an arbitrary ADL 0, Q model. In such a model, if I change this to an ADL 0, Q, I would also add gamma 2 times xt minus 2 and perhaps more terms than that. These extra terms would pop up here as well, be gamma 2 plus xt minus 2, but when I do this derivative, which is the short run effect, they are going to go away, all of them. So beta 2 will remain the short run effect that X will have on Y in all of the ADL 0, Q models. However, the long run effect will be affected. If I look at the expected value of yt and I have more lags, then you can easily see that this parenthesis will be beta 2 plus gamma 1 plus gamma 2 plus gamma 3 and so on, all the way to gamma q. And it will follow that the long run effect will be beta 2 plus gamma 1 plus gamma 2 and so on, all the way to gamma q. So let's just state these results. This is the model for ADL 0, Q. The first one is 0 because I have no lag dependent variables, only lagged X variables. The short run effect is the beta 2. That's the derivative of expected value of yt conditionally on all the X variables with respect to xt. We interpret it as the immediate effect that a change in advertisement this period will have on revenue in this period. It's short run because we know that this increase that we make in this period will not only affect this period's revenue, but it will also affect future periods' revenue. So therefore it's the short run and not the long run effect. To get the long run effect, we need to sum all the parameters in front of all the X variables. So beta 2 plus gamma 1 plus and so on, all the way to gamma q. So that was the ADL 0, Q model. So let's move on to the ADL 1, Q model, where we have one lag dependent variable, and it becomes a little bit trickier, but not a whole lot. Again, to make life a little bit simpler, let's consider ADL 1, 1 before we generalize it to 1, q. The ADL 1, 1 was this one, yt beta 1 plus beta 2 xt plus gamma 1 xt minus 1, 1 lagged x plus 1 lagged y. Notice how the presence of the lag dependent variable changes the dynamics of this model. So let's say that xt increases. The amount that we spend on advertisement increases in this period. That will have an immediate effect on revenues of the firm in this period. Moving on to the next period. Due to memory and so on, the value of xt in the previous period will have now a direct effect on y in this new period. But the new effect here is this one. So since the revenue went up in the last period, assuming that this row is positive, the revenue will increase also in this period, simply due to the increase in the previous period. You can think of this as a sort of a positive feedback loop. The simple fact that we sold more in the previous period will to some extent increase the revenue even in this period. So now in this case, there are actually two channels where the increase in advertisement in the previous period will increase revenue in this period, directly through the lagged XT and indirectly through the lagged dependent variable. Performing the same kind of analysis that we did for the ADL 0,1, the change in the expected revenue given the amount we spend on advertisement today, the amount we spent last period, and the revenue in the last period. What will happen to this as I change the amount spent on advertisement today by 1 unit? Well, the answer is still beta 2. These effects will only kick in the next period. So beta 2 will still be in the ADL 1,1, the short run effect. To figure out the long run effect of a change in the expected value of x, that is a permanent increase in the amount that we spend on advertisement, we do expected value on both sides. Expected value of yt, beta 1 plus beta 2, expected value of xt, plus gamma 1, expected value xt minus 1, plus rho, expected value yt minus 1, and plus 0. Due to stationarity, this is expected value of xt, and this is expected value of yt. So moving this term here over on the left hand side, I have expected value of yt, 1 from this term, and minus rho from this term. Then I have beta 1 plus beta 2 plus gamma 1, expected value of xt. So if I divide both sides by 1 minus rho, which is okay because I know that rho can't be 1 since I'm working with stationary data, this will be beta 1, 1 minus rho, plus beta 2 plus gamma 1, 1 minus rho, times expected value of xt. So if I do the partial derivative, what's the effect of the expected revenue if I change the expected amount that I spent on advertisement by 1 unit? And the answer is this constant here, beta 2 plus gamma 1 over 1 minus rho. And that's the important part of this model, because if I can assume that the ADL 1,1 model is a correct specification and I have data on x and y, then I can estimate all these parameters. I can estimate the beta, the gamma, and the rho, and that means that I can estimate this expression. So based on this, I can actually estimate the long run effect that a change in the x variable will have on the y variable. And this is a concept that only appears in dynamic models. In static models, since we have no lagged effects, the short run effect and the long run effect must be the same. Similarly to the generalization of the ADL 0,1 to the 0,q, it's pretty straightforward to generalize the ADL 1,1 to 1,q. So basically, to go to 1,q, I need to attach more lagged x variables here, a gamma 2 xt minus 2, and so on. That will not change the short run effect. So the short run effect for all ADL models is beta 2. For the long run effect, well, it's very similar. The only thing that will happen is that this parenthesis here will become beta 2 plus gamma 1 plus gamma 2 plus gamma 3 and so on. So we just need to hang on or attach the remaining gammas into the denominator of this expression here and here. So let's print this more carefully. We have the following. Here is the ADL 1, q model. Q lagged x variables, 1 lagged y variable. The short run effect is beta 2. The long run effect is beta 2 plus all the gamma parameters, that divided by 1 minus rho. So I will actually stop here at ADL 1, q. You can actually generalize this further to ADL 2, q and to an arbitrary ADL p, q, but the formula for the long run effect gets more complicated. So I'm just going to state that it's possible, but I'm not going to write the formula in this lecture.